Hey, welcome to the last screencast of the unit. We're going to talk about changes in oscillating systems. So it's kind of a catch-all. We're just going to look at some things that could happen in these oscillating systems. Most of the things show up on the test, so that's worth discussing. Some of them we've kind of already talked about a little bit. Let's just get going here. Okay, so when a system's undergoing simple harmonic motion, the amplitude or displacement, whichever you want to call it, is basically going to be larger when I have more mechanical energy and smaller when I have less, right? More displacement means more potential energy, and that in turn means more kinetic energy as we pass through equilibrium. So the bottom line is a small amplitude means less in me, and a large amplitude means more. And I think you already got that memo. So if I look at a graph of a oscillation over a period of time, I look at this one here, I go, you know what? I'm not seeing any diminishment or increase in the displacement over time. So that tells me that the mechanical energy remained constant. That since I always got the same amount of displacement here, that I got here, that I got here, that I got here, that I'm not losing any energy from the system. But in real world systems, it doesn't go like that, right? All these things we've been looking at are these ideal systems. We have an ideal spring that has no mass, it has no friction, and on a frictionless surface. But in the real world, there's friction. In the real world, our systems lose energy over time. And when they do, I get a graph that looks something like this, where the displacement diminishes with each cycle. Now, we call this damping. So we say a damped system. And what that means is that with each passing oscillation, work is being done by friction or air drag or something like that. That's pulling energy out of the system and making the displacement get smaller, smaller, smaller until eventually the system comes to rest. If I set a pendulum going today, by the time I came into school tomorrow, it would be at rest. So it definitely, this damping is something that is always occurring. Often we look at short time intervals where it doesn't really matter, but in the long run, it does matter. It's there. So we just want to study that a little bit. So here I have a graph, and this took me a long time to make, so I hope you appreciate it. The displacement I see is remaining constant here. Now the fact that I'm coming down to zero, this probably tells me that this is a graph of potential energy over time, right? So I have the potential energy is very high, or maybe it's kinetic energy. The energy is very high, and then it comes down here, which means that if this is potential energy, now the kinetic energy is high, now the potential energy is high, now the kinetic energy is high, but the mechanical energy stays constant the whole time. So if I don't have damping, a line for mechanical energy is going to be constant across, and it's going to touch the tips of all of these apexes that I have here. But in a damped system, I'm going to get something like this. And this graph took me so long to make. You better appreciate it. Okay, so what happens is with each oscillation, I'm losing energy. So the displacement is getting smaller and smaller and smaller and smaller. Uh, and so let's just say this is a graph of kinetic energy of a system moving across a flat surface with friction. Well, the first time I release it, I get a lot of kinetic energy, and then the kinetic energy goes to zero, but the mechanical energy doesn't go to zero because now I have a spring potential energy. Now I have more kinetic energy, but notice I don't have as much as I had before. So therefore, I have less mechanical energy because at this point, all my energy is my kinetic energy is the only kind of mechanical energy I have. And now my kinetic energy goes to zero, but my potential energy doesn't. But with each successful oscillation, my maximum kinetic energy is getting smaller and smaller and smaller. And that tells me that my mechanical energy is getting smaller and smaller and smaller as well. And eventually we'll reach zero when the system damps to zero. Okay, let's try to do a little bit of math with this. Just, try to, we know enough about work to do this here. Okay, so I've got a 2 kilogram block. It's attached to a spring. And the spring has a spring constant of looks like 20 newtons per meter, and the oscillation of the displacement of the displacements are shown here, right? So I see that the first time it went 0.5 meters to maximum amplitude, and then it passed through equilibrium and it got to 0.3. So I want to know, what is the frictional force acting between the block and the horizontal surface? I should be able to calculate it by using the work energy equation here, okay? So what I say is, I know that the work done, in this case by friction, is equal to the change in the mechanical energy. That's the definition of work. Work causes a change in mechanical energy. So in this case, that work is friction. And so basically, I'm trying to find what that force of friction is. Work equals force times distance. I don't know what the force is, but I know the distance I went was 0.5, got me to equilibrium, and another 0.3. So a total of 0.8 meters was traveled. And that's going to equal the mechanical energy of the system. Well, the mechanical energy of the system, the change in mechanical energy of the system, the best way to do it is say, Here's how much spring potential energy I had here. I know I have 20 newtons per meter of K, so I can say 1 half K, 20 newtons, times zero point 0.3 squared, because we're going to say final minus initial, and then minus the initial, which is the displacement is zero point 0.5. And when I solve this, I'm going to get uh, 0.8 meters times the force equals negative 1.6. That tells me that the force of friction is probably close to negative 2 or 2 newtons. Okay, let's try doing this now. Now I have a frictionless system, all right? And it's oscillating back and forth. And so in this position here, I've got 10 joules of spring potential energy. We're at maximum displacement of delta x, so it has no velocity at this point, so it has no kinetic energy. The mechanical energy is 10. Now, on its way back through equilibrium, it now has no more spring potential energy, but it does have all that mechanical energy is now expressed as kinetic energy, 10 joules. And we're just going to say in this case is traveling at 1 meter per second. If we wanted to, we could calculate what the mass of it is, but we're not going to do that. It keeps continuing on until it compresses the spring enough to stop the mass. So when the mass stops, it has 0 joules of kinetic energy, so it's going 0 meters per second, and all of that energy is now expressed as, once again, as spring potential energy. Now, if I wanted to find the period of this, what I would say is, well, the period is going to equal 2 pi times the square root of the mass divided by the spring constant. And let's just say when I do that, I get a period of 1 second. Okay, just for kicks and giggles. So now we're going to do the same thing, but when this thing gets to its maximum displacement, I'm going to double its mass. I'm going to put a second mass on top of it and double it. Now, at this point, that did not change the spring potential energy. So I still have 10 joules of energy in the system, but now I got twice as much mass. So when I get back to equilibrium, I'm still going to have 0 joules of spring energy, which means I still have 10 joules worth of kinetic energy. But the velocity has to be smaller. In fact, it has to be 1 over root 2 since I've doubled the mass, but I have the same kinetic energy. It's going to keep moving until it gets all the way over to here, and now it has no more kinetic energy because it has no more velocity, and it still has those 10 joules of spring potential energy that it started with. But think about this. Since its maximum velocity was only 1 over root 2 what it was before, it must have taken it longer to travel. And if we were to go ahead and calculate what happens to our period, since remember it's the period is equal to 2 pi times the square root of m over k, and since m was doubled, the period should have gone up by root 2. All right. Okay, now let's try this. All right, we're going to do the same thing here. I have a horizontal spring block oscillator, and we're just going to say, all right, here's our details. We got 100 newtons per meters of spring constant. We've displaced it 0.4 meters. It's got 1 kilogram. I just needed some numbers to work with, and if I use the formula for finding the period, I'm going to find us a period of 0.628, basically 2 pi seconds. And the kinetic energy as it passes through equilibrium is going to equal the spring potential energy here. And when I say 1 half of 100 times 0.4 squared, I get 8 joules. Now, here's what we're going to do. We're going to take this to another planet. Okay? So we're going to take it to a planet where the gravitational field strength is 2g instead of g. What's going to happen to the spring block oscillator? And the answer is nothing. Here's why. Because if I look at the period equation, g is not a part of it. The mass matters, the spring constant matters, gravitational field strength doesn't matter. It's going to oscillate in the same amount of time. What about the energy in the system? Well, the energy is just about the spring, and the displacement still has H equals nothing changed. What if there was friction in the system, though? Well, there's friction in the system. You got to keep in mind, well, the normal force is going to go from being 10 newtons to 20 newtons. So it's going to double the amount of work done by friction that would have happened on Earth. So the damping is going to happen at twice the rate. Now let's take a vertical spring oscillator and do the same thing. Take it to another planet. So remember, these are a little bit tricky. So I have this vertical spring oscillator. It has a K of 400, a mass of 4 kilograms. Now remember, when I hang this on here, it's going to fall a height, delta H. And that height, delta H, we saw the other day, is defined as this. It's 2 mg over K. So if I do 2 mg over K over here, what I'm going to find is it's going to fall 0.2 meters. All right. Now, if I took it to I'm sorry. Um, uh, So the maximum displacement is zero point 0.2. If I took it to an alien planet, I'm going to screw this up, where I had twice the gravitational field strength, what would happen? Well, instead of having mg equal to 4 times 10, it's going to be 4 times 20, which means it's going to fall twice as far. I'm going to end up doubling the distance that it falls. So it's going to displace twice as far. What implications does that have for its energy? Well, since the mechanical energy, the easiest way to find it in a spring system is maximum displacement, so it's going to be 1 half k delta h squared. So on Earth, when I did that, I got 8 joules because I got 1 half of 400 times zero point 0.2 squared. But remember, on this alien planet where I doubled the gravitational field strength, I doubled the displacement that the spring fell, so that the mass fell. So I doubled the displacement of the spring. Now remember, it's equal to delta h squared. So basically, I squared that change. So instead of having twice as much energy, I'm going to have 4 times as much energy in the system than what I had on Earth. Hmm. What about the now? Interestingly, I should point out I might have 4 times the energy in the system, but when I pass through equilibrium, the object will be traveling twice as fast because basically it's accelerating twice as fast, but it's going twice as far, and as it passes back through equilibrium on its way up or down, it's going to have twice as much kinetic energy. But that means since it's a square function, it's only going to have 2 times the speed instead of 4 times. 4 times the energy, 2 times the speed. Okay, now let's talk about what happens to the period. So on Earth, the period was equal to uh, 0.628. So remember I just said 2 pi times square root of 4 over 400, and that gives me 0.628. If I took it to the alien planet, that force of gravity didn't change that. So it would oscillate in the same amount of time. So it's basically is completing oscillations in the same amount of time, but it's going further, so it's going faster, and hence it has more kinetic energy, 4 times as much, in fact. Now we're almost done. Okay, how would the pendulum behave if I took it to a planet that had more gravity than Earth, double the gravity? So here we go. I'm going to take a pendulum that has a pendulum bob mass of 4 kilograms and a pendulum length of 5 meters. I'm going to displace it 10 degrees on Earth, and I'm going to do the same thing 10 degrees on this alien planet. Now, let's see what happens here. Now, remember, with the pendulum, the restoring force is a function of gravitation, which we just increased. So what we're going to find is this, that uh, the potential energy in a pendulum, the UG of a pendulum, is defined as mg delta h, but delta h, remember, is L minus L cosine theta. So I'm going to say mg L minus L cosine theta. I'm going to do that on Earth. I'm going to come up with this pendulum has 3.04 joules when it is at 10 degrees. If I did it on the alien planet, since I have doubled the gravitational field strength, so mg doubled, so the energy, the potential energy in the pendulum has doubled. Now remember, with the spring, it didn't change it at all, but it does change it with this. Now, uh, if the ME is doubled, the amount of energy it has at the apex is doubled, and the kinetic energy it has as it passes through the equilibrium point is doubled. What about the period? Okay, so the period, remember, is 2 pi L over G for a pendulum. I didn't change the L, but I did change the G. I doubled the G. So I should find that it should be a smaller period by 1 over root 2G, because see here, when I say 2 pi times 5 square root of 5 over 10, I get 4.44 seconds. I do that on my alien planet. Since I've doubled the denominator, I get a period of basically 3.41 seconds, which means it went down by a factor of root 2. Okay, so that's it for this unit. We're about to wrap up our semester, so please get this one in your head, and we'll get ready for our test coming up in just a few days. Thanks for watching.